Okay, so here's another finding the volume of a solid formed by revolving around a vertical axis. This one is a little different than the previous examples that I've posted. Again, give it a try ahead of time, sketch the region well, but for this one here, pay very close attention to the region and the implications of revolving this region about this vertical axis. As the problem says, find the volume of the solid formed by revolving the region in the first quadrant bounded by y equals x cubed plus 1, the x-axis, the y-axis, and the line x equals 2, about the line x equals 2. So again, please pause the video and go give this a try. Alright, so those of you who hopefully are back from trying it had some success, and if not, let's try to figure out what's going on. So here's a picture very, very roughly of y equals x cubed plus 1. It's just a cubic graph shifted upward. My drawing is a little exaggerated, and the scale is going to be off on the axes, but we're not trying to get precision in our sketch here. We're just trying to make sure that we understand exactly what is happening to the region that we're revolving. So now if I draw on the line x equals 2 right over here, this line is a boundary for the region as well as the axis around which we're revolving the region. And the region, like as it was said, it was in the first quadrant, and it's bounded by the x and y axes, bounded by y equals x cubed plus 1 and x equals 2. We get this region here that we're revolving. Now the issue that we have in revolving this region is that couple issues. One, every rectangle that we draw is automatically going to be right up against the axis of rotation. Now that's a good issue to have, because that means we don't have to deal with washers, we have to deal with discs. So this would be a disc method problem, and that's a good thing because it shortens the calculations that we need to write out. However, when I do look at all my representative rectangles, for instance, this red rectangle that I've drawn here, the right side is bounded by the axis, x equals 2, and the left side is bounded by the cubic. But not every rectangle I draw will have that property. I'm just going to put the delta y in there for now. If I draw a rectangle down over here, then that rectangle is bounded by on the right by x equals 2 and bounded on the left by the y-axis. And so that tells me that not every rectangle is formed in exactly the same way, and so now I need to draw two different volume integrals for two different regions. If you look carefully at this picture here, when x equals 1, that's the dividing line between needing the two different types of integrals, because for values, or rather for rectangles that we draw below that line, the right end boundary will be the axis x equals 2, and the left boundary will be the y-axis, or x equals 0. For rectangles drawn above that green line, or when y equals 1, then we'll have the right-hand boundary for the rectangles be x equals 2, and the left boundary be the cubic function. So we'll have to write two separate volume integrals that will combine to get the total volume of this region when we revolve it around the the axis x equals 2. All right, so with that in mind, let's see if we can continue the problem here. For the top type of rectangle here, we have this length, which is going to be the radius of the circular disc that we are going to get by revolving this rectangle around x equals 2. And since I'm dealing with delta y's, I need to solve for x in terms of y from my equation y equals x cubed plus 1. So we'll solve this for x, and I'm going to just jump down for the algebra here. You should very quickly see that x is going to be the cube root of y minus 1. And so this length here is going to be the right value 2 minus the left value, this cube root of y minus 1. That's going to be our radius for rectangles that lie above the green line, or when x equals 1. And then for the rectangles that lie below, this is pretty straightforward. They just all have a radius of 2. All right? Or in other words, the region that lies from that line and below would just, when we revolve it, it's just going to be a cylinder of radius 2 and a height of 1. So we could actually just use regular geometry to do that now that I think about it, but I'm still going to set up a volume integral because that may be asked for on the AP exam. So now that we know our two different radii for the two different regions, let's go ahead and see if we can start writing the area of the cross sections. So for the cross section here, the area of the circle, and this is when y is greater than 1, we get pi times the radius squared. The radius, as we saw, was 2 minus that cube root, and the cube root was of 1 minus y. So we'll have pi times 2 minus the cube root of the quantity 1 minus y, or y minus 1. And then for the area of the cross section when y is less than 1, we'll just have pi times the radius squared. The radius is 2, so we get 4 pi as our area for that region. Now just to consider upper and lower limits of integration. For the first region, as we can see, we're going from 0 to 1, and from 0 to 1. Those will be our upper and lower limits of integration right here from 0 to 1. And then the second integral will go from 1 all the way up to, well, I need to figure out where or what the output is, what the y value is here when x equals 2. All right. So from our equation here, y is equal to 2 cubed plus 1, we're going to get y equals 8 plus 1, or y equals 9, as the y value of the cubic when x equals 2. So our second integral is going to go from 1 to 9. All right, so using those two expressions for our areas, let's write our volume integral. So our integrals, the volume will be the definite integral from 0 to 1 of 4 pi dy. Remember, that's just the volume of a cylinder, radius 2, height of 1, but we're using a volume integral to represent that. And then the second integral is the integral from 1 to 9 of pi times our radius, which was 2 minus the cube root of the quantity y minus 1, and then all that is squared, and dy. Alright, I'm just going to go back and double check to make sure I didn't mess anything up. So we can see lots of principles happening here. We're using our disk method. We have our right minus left. We have to use two separate integrals because the rectangle's boundaries change for different regions. So this is contains a lot of good properties here that would help you really understand these volume integrals. We're not going to worry about evaluating that. You can do so on your calculator. If we had to do so by hand, we could. I just wouldn't want to, at least not right now. All right. Keep practicing.